100 billion parameters on a CPU. Microsoft's official BitNet.cpp repository now benchmarks a 100 billion parameter model at 7 tokens per second on a standard consumer CPU. This is not a compression trick. It is a structural rewrite that eliminates floating-point multiplication from the transformer block. By June 2026, the shift from VRAM-bound inference to simple integer addition has moved from a research curiosity to a deployment reality for hardware with limited memory. This performance level on a single chip indicates that the era of requiring $80,000 GPUs for high-parameter inference is hitting a technical wall. Here is the math behind the ternary mechanism, the death of floating-point multiplication. BitNet B1.58 relies on ternary weights, where every parameter is restricted to just 3 values, -1, 0, or +1. From an information theory perspective, this requires log base 2 of 3, or roughly 1.58 bits per weight. The computational payoff is massive. Because weights are ternary, the standard dot product operations in self-attention are replaced by simple integer additions and subtractions. Benchmarks from May 2026 show this reduces arithmetic energy consumption by 71.4 times compared to 16-bit baselines. We are essentially trading high-precision floating-point units for raw integer throughput, which is why modern CPU extensions are finally outperforming enterprise GPUs in latency per watt. But there is a significant hurdle in how these models are built. The high cost of training from scratch. There is a significant caveat. You cannot simply quantize existing Llama or GPT weights into this format. Post-training quantization effectively fails at the 1.58-bit level, where perplexity spikes exponentially. BitNet requires training from scratch, using specialized bit-linear layers that handle the straight-through estimator during backpropagation. Furthermore, while the CPU performance is validated, NPU support remains fragmented. As of early June 2026, successful 2 billion parameter deployments on Qualcomm Hexagon require custom kernels that are not yet part of the main branch. This creates a barrier where only teams with massive compute budgets can build these ultra-efficient foundational models. This shift leads to a new way of measuring model efficiency, the intelligence density frontier. The takeaway from the last month of BitNet updates is that we are moving past simple compression and into the era of native low-bit training. By moving the bottleneck from VRAM capacity to memory bandwidth, models like the new Bonsai 8B series prove that reasoning capabilities do not require 16 bits of precision, they require architectural density. For builders, this means the reliance on high-end GPU clusters for inference is ending, not because hardware got cheaper, but because the software stopped asking for flops it did not actually need. This creates a divergence between training clusters, which still need high-precision silicon, and the edge, which is pivoting toward integer-only architectures. Watch the integration of BitNet kernels into standard mobile chipsets over the next quarter. When the hardware catches up to the ternary math, the economics of local agents will move from experimental to the default deployment standard. Subscribe for more